This is going to be 10.5, polar form of complex numbers. So we're kind of skipping around from the book, which is fine. We're going to come back to the other chapter of polar graphs a little bit later. So here what we're going to do is we're going to talk a little bit about complex numbers. So if you remember what a complex number is, it's basically the letter I. So so far what we've kind of said is that, let me get rid of this. That's wrong. If I said that I had the square root of -4, we would usually say that this is no solution because you can't have a negative inside of the square root. Okay, but usually if we extend this now from the real numbers to the complex numbers, this does have a solution. So the square root of -4 actually is equal to 2 times I. And here, I is just equal to the square root of -1. So it's what we call an imaginary number. So a complex number basically has the form of a plus bi. So for example, if I have 2 plus 3i, this is what we call a complex number because we have two different forms. This is what we call the real part, and this is what we call the imaginary part. So you've kind of learned this in algebra before. So complex numbers here can be added, subtracted, multiplied, and divided. So let's do a little recap. So let's say you have two different complex numbers. Okay, so you have 3 minus I, and you have another one, 5 plus 2i. So here what we want to do is you want to add them both together, you want to subtract them, multiply them, and divide them. Okay, and then graph the above complex numbers. So in order to add them, that's pretty basic. So what you got to do is you're going to take both complex numbers, 3 minus I, and you're going to add them to 5 plus 2i. And all you really have to do is just combine like terms. So I'm going to take the 3 and the 5. That's going to give me an 8. And then you're going to have this -1 plus positive 2. That's going to give me a positive 1i. And this will be the solution. So you're basically kind of just combining the like terms. So now let's look at C1 minus C2. So you're going to take 3 minus I minus, and then you're going to have 5 plus 2i. So here what you can do, before you can do that, let's distribute this negative out. So you're going to have 3 minus I minus, oops, let's get rid of that parenthesis, minus 5 minus 2i. So here let's do this. So 3 minus 5 is going to give me -2. And then the -I minus 2i is going to give me -3i. So that's going to be the subtraction of the two complex numbers. Now what we're going to do is multiply them. So I'm going to multiply 3 minus I, and then 3, oh, that's wrong, 5 plus 2i. So what we're going to do is FOIL everything out. So you're going to get 5 times 3, 3 times 5 gives me 15, plus 6i minus 5i minus 2i squared. Okay, so here we're going to have 15 plus 6i minus 5i is going to give us 1i minus 2i squared. Now let's think about that. What does I squared really do? Well, if I is equal to square root of -1, I squared is basically squaring this guy. So remember, the square and the square root is going to go away, so I squared is equal to -1. Okay, so make sure that you know that. I squared equals -1. So let's go ahead and plug that in. So 15 plus I minus 2 times -1. So this is going to give me 15 plus I plus 2, which is going to give me 17 plus I. Okay, so don't leave the I squared there. Make sure that you plug in the fact that it's equal to -1. And then finally, let's just divide it. So C1 divided by C2. Okay, so we're going to take 3 minus I, and we're going to divide it by 5 plus 2i. And the way that we're going to do this is we're going to multiply by the conjugate. Okay, so if you remember what the conjugate was, you're just multiplying it by the division of 5 minus 2i. And this is what we call the complex conjugate. Okay, so you're basically just multiplying it like that. Okay, so on the top part, you're going to have 3 minus I, 5 minus 2i, divided by 5 plus 2i, 5 minus 2i. Okay, so now let me FOIL everything out. So we already know what the top part is, because the top part we just FOILed everything out with that, but there's a minus, so we have to be very careful. So let's just do it again. So this is going to be 15 minus 6i minus 5i plus 2i squared. This is going to be divided by the bottom part, which is going to be 25 minus 10i plus 10i minus 4i squared. So you can kind of see that this goes away, and I'm left on the top with 15 minus 11i plus 2i squared gives me -1, divided by 25 minus 4 times -1. Okay, so on the top, this is going to give me -2. So on the top, you're going to have 13 minus 11i. And on the bottom, this is going to give me a +4. So that's going to give me 29. So the way that you write that is, let's give the 29 to both of these terms. So you're going to have 13 over 29 minus 11 over 29i. So in the end, what you kind of want to have it as is in the form of a plus bi. Okay, that's kind of how you want to be able to do it. So division usually takes a little bit of time because you got to multiply by the complex conjugate. So, but other than that, it's nothing too difficult. So one thing that we want to be able to do is draw this. Okay, so let me draw it in orange. Okay, I don't know if I have enough space, but let me go a little bit over here. So basically drawing this, the way that you kind of want to do it, let me erase this part. Erase. Okay, so the way that we draw a complex number is the same way that we've been drawing regular curves or like the regular Cartesian plane, the rectangular coordinates. So basically, you have your x and y axis, but now your x-axis is what we call the real part of the imaginary number. I'm sorry, of the complex number, and then the y-axis is the imaginary part. So if you think about it, the real part is going to be 1, 2, 3, 4. So basically just the regular numbers, -1, -2, -3, -4. Let me give you -5. Also 5 over here. And then here you're going to have the imaginary numbers. So I, 2i, 3i, you know, so on and so forth. And then here, -i, -2i, -3i, and so on and so forth. Okay, so it's basically kind of the same. So now let's go ahead and graph them. So C1, so Z1 is going to be 3 minus I. So this part is the real part, and this guy is the imaginary part. So here's the real part of Z. So the real part and the imaginary part is what we're going to graph. So the real part is 3. So here we're going to go 3 units this way, and then minus I. So that's going to be down here. So this point corresponds with C1, which is 3 minus I. Okay. Okay, and now what we're going to do, let's graph the other guy. So let's graph this guy. So this is the real part. So the real part goes up to 5, so 5. And then the imaginary part of this guy, maybe I should write 2, and this guy's 1. It's going to be 2i, so it's going to go up to 2. So it's going to be up here. So this point is going to be, C2. Okay, so graphing them are not that bad as long as you know where the real axis is and the imaginary axis is. All right, so what is the whole point of this? Well, the whole point of this is that we're going to use trig to kind of be able to represent these complex numbers in a different form called polar form. Now, right now, polar doesn't really mean anything to you. The last section, which is polar coordinates, will kind of make a little bit more sense. But for right now, we're just going to call it polar just for the heck of it. So what we're basically going to do is we're going to break up these complex numbers and write them into something called trigonometric form or polar form. Okay, so let me give you a couple of some definitions. So we can rewrite a complex number in terms of trigonometric functions that make computations easier. Okay, so when we multiply a complex number and a complex number, you can see that it can kind of make things a little bit harder. Same thing with division. So by transforming them into trig form or polar form, basically we make them a lot easier to work with. So the first thing to kind of define is what we call the modulus. So the modulus of a complex number. So another way to kind of think about the modulus is kind of the absolute value of a complex number, but it's just a fancy way to just say that. So basically it's just a distance from the origin. So if I had an imaginary number right here, so here's the real part and the imaginary part, then the distance from the origin to that will be the modulus, and we kind of symbolize it as the absolute value of z. And we also give it another name, which is r. So here, the way that you do it is that if you have this complex number in this form, x plus yi, then basically all you got to do is take the square root of x squared plus y squared. That's basically all it is. Okay, and I write it here. It's also called the absolute value. So also another way that we can kind of talk about it is also in terms of the angle theta. Okay, and theta is basically the rotation from the x-axis to that particular, to the modulus itself. So this angle theta is what we're going to call the angle. Okay, so basically the polar form of this equations are this guy: x is equal to r cosine theta, y equals r sine theta, and r equals square root of x squared plus y squared. So where do these formulas come from? So they're actually really easy to derive. So let's say, for example, you have this particular point in the real and the imaginary plane. Here you have the value of r. Okay, so it was basically the modulus, the distance from the origin all the way to this point. You have your x coordinate and you also have your y coordinate, okay? And then this is the real and imaginary axis. And then also you have this angle from the x-axis all the way until that particular point. So where do these formulas come from? Well, first let's go ahead and try to find the cosine of this angle. So we know that the cosine of theta is going to be equal to this x divided by this r. Notice that if I move the r over, then you're going to have x is equal to r cosine theta. So that means your x coordinate is going to be equal to r cosine theta. Okay, that's basically it. What about if I wanted to find the sine? Well, the sine is going to be equal to the y over the r. Move the r over, you see that y equals r sine theta. Okay, which is basically our second equation. The other equation arises from the fact of using the Pythagorean theorem. We know that x squared plus y squared, okay, is going to be equal to r squared. And notice that when I take the square root, r is going to be equal to the square root of x squared plus y squared. Notice that we're not writing plus or minus because r is going to be the hypotenuse, and the hypotenuse is always going to be positive. So that's where that y comes in. Later on, we're going to also use this guy. Tangent of theta is equal to y over x. Keep that in mind. We're not really going to be using it just yet, but keep that in mind that we can also use the tangent of theta equals y over x to solve for theta or anything else. Okay, so this is basically a little bit of the derivation of some of the complex numbers, x plus yi, and be able to write it into r and theta. Okay, so this is basically just saying what you can do. So if you have a complex number, z is equal to x plus yi, then basically what you can do, since I know that x is equal to r cosine theta, and I know that y is equal to r sine theta, then what we can do is just basically plug them in. So in here, I'm going to plug in x, r cosine theta, and for y, I'm going to plug in that guy, which is going to be r sine theta. So I'm basically plugging them in, and I'm putting the I in the front. So then what happens here is that I can factor out an r because they both have like terms. So that's where this r comes from. And in the inside, you're left with cosine theta plus I sine theta. So basically, the way that you write this, the polar form, this complex number is going to be r cosine theta plus I sine theta. Okay? A short way to write it is this way. Z is equal to r cis theta. So basically, this cis, C stands for cosine, I stands for the I, and then S stands for the sine. Okay, so, and then a theta. So it's just a short way to write it. Now, keep in mind that in WebAssign, if it does not accept it as cis, it might accept it as the long way. So just keep that in mind when you're doing problems like this. So in the next video, what we're going to do is do a couple problems using these formulas.